Okay, hello. So we're going to continue with our discussion of electrochemistry, and we're finishing up this chapter talking about electrolysis. So far we've been talking about galvanic cells and standard reduction potential and how to do calculations within that. And now we're going to look at electrolysis, which is almost the reverse of a galvanic cell. So we're going to talk about an electrolytic cell. So electrolytic cells use electrical energy to produce a chemical change, so the reverse of a galvanic cell. Electrolysis is the forcing of a current through a cell to produce a chemical change for which the cell potential is negative. So if you remember from galvanic cells, we wanted the cell potential to be positive overall. So electrical work basically causes a non-spontaneous chemical reaction to occur. So non-spontaneous, we're going the opposite direction of a galvanic cell. This would be similar to charging a battery, producing aluminum metal, or chrome plating. These are all examples of using electrolysis. So in an electrolytic cell, everything is basically opposite. So electron flow is opposite, the anode and the cathode are reversed, and the ion flow through the salt bridge is also reversed. So just basically flip everything in a galvanic cell. Okay, we can use electrolytic cells and stoichiometries to solve for different quantities. So let's say you wanted to determine the mass of copper that was played out when a current of 10 amps. So remember, the symbol for amp is A, and an amp is 1 coulomb per second. Is passed for 30 minutes through a solution containing copper 2+ ions. Okay, well here's our half reaction for the reduction, gaining of the electrons. First thing we're going to do is use the amps and time to find coulombs. So we would take the 10 amps for every 30 minutes, and we would convert that into coulombs per second. And then from there, we could use Faraday's constant, which is 96,485 coulombs per mole, to convert coulombs to moles of electrons. So we'd have some number of coulombs, and then we'd use our 96,485 coulombs for 1 mole, and that would give us moles of electrons. Then we could use our half reaction and the number of electrons that were transferred to go from moles of electrons to moles of Cu. So we know for every 2 moles of electrons, there's 1 mole of copper. And then we could use the atomic mass of copper. So for every 1 mole of copper, there's, I don't even know, 60-something, we'll just put 60 grams of copper, and we can convert that from moles to grams. And so that's how we can use an electrolytic cell with stoichiometry. We're going to do an example, but this example is going to be the reverse of what we just talked about. Okay, so we want to know how long must a current of 5 amps be applied to a solution of silver ions to produce 10.5 grams of silver metal. So we're looking for time, and we're starting with mass. So it's basically the reverse. So first, let's take our grams and go to moles so that we can use our half reaction, which we'll need to also look up. And our molar mass is 107.868 grams of silver. Remember, this just comes from the periodic table. In 1 mole of silver. And we can actually do this in one full step. If we look up the half reaction for silver, it's the silver ion plus an electron going to just silver. So for every 1 mole of silver, there's 1 mole of electron transfer. And then I know for every 1 mole of electron transfer, there's Faraday's constant, which is my 96,485 coulombs. And then I know that 5 amps is 5 coulombs, 5 coulombs per second. So for every 5 coulombs, that's 1 second, and that'll give me time, which ends up being, I've already done the calculation, 1.88 times 10 to the 3rd seconds. You could also put this in terms of minutes, 31.3 minutes. So grams to moles, moles of silver to moles of electrons using the half reaction, moles to coulombs using Faraday's constant. An amp is a coulomb per second, so 5 amps is 5 coulombs per second, and that gives us our time unit. Okay, so let's look at some other uses of electrolysis. One is the electrolysis of water, and we can use the decrease in free energy caused by the spontaneous combination of hydrogen and oxygen gas to form water to run a fuel cell and produce electricity. So we can also do the reverse process where we take the water and we split it up into hydrogen and oxygen, and this is through electrolysis. So on the anode, we have the water going to oxygen, 4 hydrogen ions, and 4 electrons. And because it's the anode, it's the negative cell potential. The cathode is the water plus 4 electrons going to hydrogen and hydroxide. And you can see that this is less negative. for our cathode. And then in that reaction we have water going to hydrogen, oxygen, and then 4 waters but in ion form, hydrogen and hydroxide. Electrolysis in this case won't occur unless we have a small amount of soluble salts, so you need some sort of ions to get this to occur. And there's also a video here that kind of demonstrates this, so we'll go to this next.
In that small plastic container are 2 metal push pins, and they're inserted a distance that's between the positive and negative lead of the 9-volt battery. So you just insert them in there and make sure that they're that distance apart, and that should be fine. In the container is going to be some water that has baking soda mixed into it. The baking soda in the water allows electricity to flow between the 2 metal tips of the push pins. And so now you set them on the leads, and the electricity can flow between the 2 push pins now. And so electricity is flowing through the water, and so that's enough energy to break apart the water, make it undergo a chemical reaction, so that the H2O gets broken apart into H2 and O2. It's going to be hydrogen gas and oxygen gas. And both gases are going to flow up through the test tubes, and one of the gases is going to be in one test tube and the other one's going to be in the other one. How do you know which one's which? Well, if you take a look at the amount of gas in each test tube, it's going to be twice as much hydrogen gas as oxygen gas. So you can see in the right test tube you have twice as much hydrogen gas as oxygen gas. This is how experimenters first learn that the ratio of hydrogen atoms to oxygen atoms in water is 2 to 1. It's 2 to 1 ratio, thus H2O.
Okay, so we can also show electrolysis of different mixtures of ions. So in a mixture of ions, how do you determine which ion is going to plate out onto the electrode first? Well, you base this on standard reduction potentials. So the more positive the standard reduction potential value, the more the reaction has a tendency to occur in the direction indicated, meaning it's going to plate out first. So let's look at an example of that. Okay, so we have an acidic solution containing solarium ions, VO2+, and iron ions, and using the standard reduction potential values, we want to give the order of oxidizing ability of these species and predict which one will be reduced at the cathode of an electrolytic cell at the lowest voltage. Okay, well, we can see that our smallest reduction potential is, our smallest reduction potential is iron, and our largest reduction potential is solarium. And so that means that this one will be the best oxidizer, and that means that it is going to be reduced first at the lowest voltage. And so solarium, and then the VO2, and then our iron. Okay, so our highest potential means it's most likely to get reduced first. Okay, so one of the other things that we have to consider is what's called overvoltage. So if we look at the electrolysis of an aqueous solution of sodium chloride, we can use the standard reduction potentials to predict the products. And all of these have been written in terms of oxidation. And so if we look at our 2 reactions, we can see that for chlorine it's larger. That means this one will get reduced, which means that this, the water and the oxygen, is getting oxidized. So we would expect that O2 would be produced. But in reality, this doesn't happen, and this is due to what's called overvoltage. This is the voltage required in excess of the expected value. So this water to oxygen requires more voltage than what is expected, and the causes of this can be very complex. And so you just need to keep in mind that you need to use standard reduction potentials cautiously. We can use them as kind of a starting point and to make some approximations, but it's not always going to be exactly how things work. Okay, some other common electrolytic processes are the production of aluminum, the electrorefining or the purification of metals, metal planing, and electrolysis, like we just looked at, of sodium chloride. Okay, so this is the homework that we're going to practice. We'll also discuss this in class. Have a good day.